Hello, welcome once again. Previously, I made a video about how to test an alternator. The problem is for today's alternators, they are computer controlled. As opposed to years ago, 20 years ago, you just have to worry about changing the alternator and the diodes inside. Today, it's much more advanced than that. Now, to try to simplify what's going on and how computer makes decisions, when you troubleshoot, you have to come to some different conclusions. Now, this is what's inside the alternator. Okay, let's start from here. There's a rotor, there's a stator. These are the windings that are stationary. Inside is a rotor. You could think of it as a component that's turning, that's creating a magnetic field to the stators, which is the windings, and that produces an AC voltage. Now, that AC voltage is not good enough to to go back to the battery to charge it. So here's the battery. Okay, here's what's inside the alternator. Three parts: the AC generator itself that forms the AC voltage, a regulator. What does regulator mean? Regulator means when you put a load on something, when you have a power source. It could be a battery, it can be an actual DC supply or AC supply. You have to make sure that that voltage stays constant regardless of the loads that you put on it. And what is the load? The load is the light systems, the fan motors, anything that requires current, that is pulling current. So therefore, let's say the modules, the computer modules, all these things, fuel injectors, they are requiring current. They are the load on the alternator. The alternator has to make sure that this voltage output of the alternator is constant. Let's say it'll be, make it easier, 14 volts. Let's make it easier. Output is 14 volts of this. Okay, so DC is over here. This is the output of the alternator. Let's say it's 14 volts. Okay, roughly 13.6 to 14.5, depends on temperature. But for our purposes, we're going to make it as simple as we can. So AC generator is creating the AC signal. Now, this is not enough to go back to the battery. Why? What's the battery? The battery is a DC voltage, a DC power source. Can we charge a DC voltage of the battery with an AC generator output? No. We have to change this AC generator output, which is a sine wave, to a DC voltage. Thus, we have something called rectifier bridge. These are 6 diodes which will rectify or change the AC to make it simple to a DC voltage. Okay? So the output of the alternator originating from an AC generator signal, which is not good enough for us to charge the DC battery, has to be rectified or changed to a DC voltage. These are the roles that the rectifier bridges play to change this to DC. So now the 14 volts DC can become an actual 14 volts DC voltage. That's good enough to charge the battery and to keep the accessories going. Now, I just brought up the point, a regulator. What is a regulator? This is 14 volts DC. I'm going to look at the gauge on my car. It's going to be 14 volts DC. I'm going to put on the headlights. Will this drop? No. I'm going to put on the fan motor, which requires 20 or 30 amps of current. Will this drop? No. I'm going to put on maybe the cameras that I have in the car. I'm going to put on, let's say, the radio or whatever. Should this drop? No. This should be 14 volts, as I mentioned, for all those accessories I just put on. What is responsible for keeping that constant at 14 volts or 13 volts, whatever? This is the circuit. So this is the AC generator. This is the rectifier to make sure that the rectifier changes it to DC, which we need to charge the battery and to go to the computer modules, fuel injectors, ignition system, make sure everything is DC. But we have to keep it constant, regardless of the load condition. So you crank and you go to, let's say, 2,000 RPM. This is the way we usually test. 2,000 RPM. I like to go 2,500 RPM. I like to put all the accessories on that I just mentioned. Headlights, motor, air conditioning, everything goes on. Cameras, speaker system, whatever I have. And I'm going to look for that gauge in that car, making sure it's constant at 14 volts. What does that tell me? That tells me this part of the circuit is working. The regulator, that's what it's called, the regulator, is working. So fine, we'll give it a check. So we have a method of figuring out if the regulator is working. How? By putting a multimeter and measuring 14 volts. Great. What about the current output? At the same time that this is keeping the voltage output of the alternator constant, there is a current. This regulator, I don't want to get too technical, with this transistor and the Zener diode. This TR2, actually, the collector and the emitter, the load for this is the resistor, but also the load for it is what? Come back to the rotor, is the rotor itself. The winding of the rotor is a load for it. The resistance will change, the current will change, but the voltage will remain the same. The current will change of the output. Okay, so let's make it simple. I'm putting my multimeter at this wire. And what is this wire over here? This is the thick wire that you see coming out of the terminal of the output. So in that video that I made, how to test an alternator, I took a multimeter and I measured the output of the alternator. And what was I expecting to get? All right, let's say 14 volts DC, okay? That's that thick red wire. But that didn't suffice to me, because what about the current? Remember, this is computer controlled. The computer is controlling the current. The computer is controlling the voltage. So the voltage, we know. We found a method how to test it by a multimeter. Simple. How do I test the current? The current is changing when, as I'm putting on more accessories, the demand is more. So what did I do? I took a clamp meter. This is a clamp meter that you put around the wire, the conductor in that video. That's what I did. I put this around. This has a magnetic field around it, which induces a current. That current is being over here. In this wire over here, I can detect the current with this clamp meter. I don't have to open the circuit. I just put it around that fat red wire, which I did in the video. Okay, I noticed as I put the headlights on, right, it went up, let's say 15 amps. So I had 10 amps, maybe it went up to 25 amps. What does that tell me? That tells me the computer is changing the rotor, the field current, and when the field current changes, I detect it by what? By the clamp meter that I just used, and the current went up from, let's say, 10 amps to 25 amps. That's a good indication that the computer is giving a command. The alternator is receiving that command. The alternator is acknowledging that command. How do I know? Because the current went up. Remember, the voltage stayed the same. So what is that telling me? I can't really tell what's going on. I could just tell the regulator is working. But I want to tell if this rotor and stator, if the current is changing as I put more accessories on. And that helped me by putting on what? This clamp meter around the wire, that red wire, and I see that it goes up. That means the computer is giving a command, alternator is listening to the command. Okay? Now, we're not done yet. We're not done. So we figured out two things that have to be done for these computerized controlled alternators. In the olden days, 25 years ago, you went alternator, right? It was 14 volts. It was 12. Instead of 14 volts, it was 12 volts, right? What do? You just change the alternator. Easy. No, you can't do that today. You have a computer, you have a module, you have a regulator, you have a rectifier. You have much more than you had 25 years ago. That technique does not work 25 years later. That's why I came up with this to measure the current. I want to make sure the computer gave the command when I put the headlights on. The alternator or this circuit received the command, and what? And it took and acknowledged the command by giving and increasing the 25 amps to let the headlights go on. Okay? Now, as we just said before, things have changed, computer has changed, right? What do we do? And now, the computer has a signal. That signal is called pulse width modulation. Not to get too technical, but you see, this is a very technical subject. Whenever I get the emails, all I get is people saying, you know what? I drove the car, right? I drove the car, and after a while, I headed back, and you know what? It stalled, or obviously shut down. Okay, was not able to start it back up. I don't know what it is. So the alternator will do that, obviously. If the alternator, instead of 14 volts, right, you first start up that car, how much is the battery voltage? It could go down to 10.6 volt, 10.5 volt, 10 volts. So here it is over here. Right away, the alternator has to do its job to bring this back to charge this battery back to 12.6 volts, whatever, right? Okay. Now, it's something called pulse width modulation. Okay. The on time and the off time. The on time, this is a pulse, is 50% in this example. How much is the rating of your alternator? Let's say it is 100 amps. It can give out 100 amps, okay? Some can give out more than that, okay? But let's just use an example, okay? 100 amps. In the beginning, I crank that car. I crank it and crank it, right? In the beginning, it has to charge that battery. There's a lot of current that has to charge that battery. How is that demand from the computer given to the alternator? By the pulse width. Let's say 100 amps. Let's say it needs 70 amps in the beginning after you just cranked it. 70 amps. Charge the battery, keep the accessories going, fuel injectors, ignition, if you have coil on plug, whatever your fuel injection system, a GDI system, whatever you have, that system, the fuel injection system. Let's say I need 70 amps. So 100% is from here to here. That's 100 amps. 70% of this pulse, if this will be on, here is the on time. This is the off time. This will increase. So instead of 50%, this might go to what? 70%. Here's 70%. Okay? If you need 100%, 100 amps from the alternator to give that demand of current, I might be 100%. Where will I be? I'll be over here at 100%. If I need 50 amps, where will I be? Right here where this example is. This will be 50% the pulse. So the pulse will change according to demands of the load from the computer. Okay? 70 amps, I'll give 70% on time. 50 amps, I'll give 50% on time. 100%, I'll give 100%. As the battery is charged, you need less and less pulse width to charge the battery and to keep it going. Now, how do you measure that? You have to measure this. Now, the problem is you need a scope. But I realize that most of the people, the viewers, are not familiar with scope and how to use scopes. This is the difficulty. How do you teach a technical subject of electronics and try not to use certain equipment, test equipment, electronics that you have to use? How do you do that? How do you tackle that subject? This is the difficulty that I always have. So I came up with, if you saw in that video, how to test it with the clamp. The clamp meter, not this one, has a duty cycle. Pulse width duty cycle. It'll tell you how much you're reading. It'll tell you 50%, 70%, 90% in that video. That's why I did that video. So now, put the headlights on, put the motor on, What would you see when you put the clamp on? You'll see 50% going up to 70% or 90% by the readout of that clamp meter, because you have to do that. So far, we have to do three things. Make sure the current output of that alternator, the voltage is constant with the multimeter, the current output with the clamp meter, and also a clamp meter or oscilloscope, which is the best, but 50% that will tell us duty cycle. What else do we need? What else do we need for these computerized things, right? There's a thing called ripple. Ripple, if you change a voltage to DC, it is flat, level. But in technicality, it is not what it seems, okay? This is what comes up, ripple. It's not a perfect level of DC. This over here, up to here, is called the ripple. You don't want so much ripple. That means that the output from that alternator has too much ripple. Now, the example of the scope, and let me go to that example that I can show you. Okay, this is called a ripple for an alternator. We like this one, but this is without a load. You see these? Like this? This is the ripple in millivolts. You see this? This is with a load. What happened? You got a spike. It's almost the same thing, but you got a little spike. Okay? These are not even. These are even. That's what happens when you put a load. Let's say you have a bad diode that I just spoke to you about. What happens? Look at the difference. You're missing a loop, a cycle. You know right here, either you have a bad winding or you have a bad diode. Here, as you can tell over here, it's an open diode or other winding problems. So this is the pattern we want, but of course I realize people are not familiar with scopes. How can you go about it? Again, as you see in the video, I put it on AC volts. When I put on AC volts, even though it's a DC volt output, I should not read any ripple. This is ripple. I should read it in the millivolts. I should not read anything higher than that. So that's a good way to figure out everything. Okay? Now, there is one more. That wire that I just told you, that thick wire, I don't want any voltage drop across it. From the DC output of 14 volts, I don't want, let's say this is 12 volts. This is the sensing voltage, okay? This will sense how much voltage there is of the battery. Okay? 14 volts or 13 volts, 16 volts. 16 volts, it is overcharged. You cannot overcharge the alternator, the battery. You cannot undercharge the battery. Those two things. Now, I don't want a voltage drop from here back to the battery. I want 0 volts. If I put a multimeter here, which I did in the video, and I read 0.5 volts, 0.6 volts, too much. This cable has too much voltage loss in it, of a voltage drop in it. I don't want that. That's one thing you have to check for, and that's what I did in the video. So go to Joe Electronic Schematics for Auto, and you'll see that. One last thing, and you'll see how complicated it is nowadays. You just can't make a call and say, alternator is bad, which I get all the time. What do you think the problem is? I already changed the alternator. What do you think it is? Well, it's computer controlled. The scanner, if you have a bidirectional scanner, I can give a command to turn on the pulse width, the alternator, and I could play like the computer. I'm the computer with the scanner. I'll give it an on time and let it see if it produces more pulse width by the scanner. It's called a bidirectional scanner. But I realize most of us don't have it, the viewers. So we have to try to keep it simple, even though it's a technical. Now, temperature plays a role with the output of the alternator. So, looking at this graph, okay, what do you see over here? At 20 degrees Fahrenheit, look at the minimum and maximum. Go to 140 or over 140. What do you see? You went from 14.3 to 15.3 to less than 13.8. So what do you see? The hotter it gets, the less the output. So let's think of an example. In January, do you think the voltage will be higher or lower? In January, in Chicago, in Green Bay, guess what? That voltage will be much higher. according to this graph. Why? Because it's a temperature compensator. The colder it is, the higher the output voltage of the alternator. The warmer it is, the less the voltage. Okay? Now, I understand this is technical, and that's why go to the video and you'll understand why I did what I'm doing. You cannot just look at a gauge and say 14 volts, 12 volts, alternator is not good. Let me go AutoZone and pick up an alternator. That was 25 years ago. That's not for today's electronic vehicles. Okay? So, as I said before, these are the methods that I use. The current meter to measure current. AC voltage for ripple. Duty cycle. Okay? And of course the DC output. All these things have to be done in order to have an accurate diagnosis for an alternator for today's vehicles. Okay, so I hope this helped, and I realize it's a lot of technical support, but this is what we're dealing with computers nowadays. It cannot be easier than this, unfortunately. Okay, thanks for watching.